In this video, I want to cover how to convert old mechanical keyboards such as this one from an unknown protocol into something like USB so that you can use it on the modern computer. To understand the components that we want to find on a real keyboard PCB, I'll first review the basic operation of a keyboard matrix scan. We'll use 5 volts for the logic levels, as this is what vintage electronics usually have. We have 2 output pins, 2 input pins shown as columns. By default, we'll also assume external pull-up resistors for 5 volts. So I marked 2 switches, top left and bottom right, as closed. So now we can loop through the rows and set the current row, in this case row 0 output, to low state. Then we can check each of the input pins in order. So marked in red, the first switch is closed and the output is low, so we can read 0 on the input pin. The second switch is open, so the value is 1. To scan the next row, we revert the output of row 0 back to 5 volts, and then we set the output of the second row, in this case row 1, to low, and repeat the same process as we described before. So now even though row 0 column 0 switch from the previous scan is closed, because the output on row 0 is 5 volts, it does not matter. Since row 1 column 0 switch is open, the result is therefore 1. For row 1 column 1, the switch is closed and output is low, so we record a value of 0 in this case. For these older boards, usually for the 1980s and 90s era, we usually have an Intel 8048 or 8049 series microcontroller, and on the side we usually have some extra chips if the matrix is extra large, such as the one on this board. So this keyboard has quite a lot of keys, which means that generally you may want to save some input and output pins on the microcontroller itself by using some extra decoder and mux chips. So here is a direct camera shot of the back of the PCB. This keyboard is a more complex layout as it doesn't map rows and columns directly to the CPU. We mentioned earlier a set of decoder chips and input selectors. These reduce the number of I/O pins required on the microcontroller for a very large matrix layout. Both the 74LS series chips, in this case, are output selectors, and the 74HC151 chip is an input selector. With this information and the series of pull-up resistors next to the HC151 chip, we can have some good hints as to how to map out this circuit. Here's a quick schematic I made to visualize the connections between the microcontroller and all of the decoder chips. It's important to note that mapping out the entire switch layout is very time-consuming and not necessary for the methods I will show in this video. In this case, the keyboard has 5 output selection pins and 3 input selection bits. Now this should look more familiar to the diagram we showed earlier. We can now desolder the microcontroller and drop in a 5-volt compatible controller such as an Arduino Pro Micro. So in summary, we only need VCC 5 volts, a ground connection, 8 input and output selector I/O connections, and of course D+ and D- pins for the USB. This matrix is 19 by 8 keys, giving us a total of 152 possible keys, using only 8 I/O pins plus 1 input pin for the key read result. If your keyboard circuit is much simpler, you can probably eyeball the PCB to find the column and rows directly connected to the CPU. So in this example here, I guess it saves a lot of time finding the circuit connections, but means you will have a lot of fun soldering about 12 to 25 I/O pins to a microcontroller. So now we can plan our microcontroller swap now that we have the old CPU out of the way. So as before, we have the row selection, the column selection, as well as 2 data pins for the USB, VCC connection, and also a ground. And on the left side here, I determined 2 paths we can connect to carry the USB D+ and D- connections from the cable connector to the Pro Micro. This requires removing the old capacitors and resistors in the path of these 2 traces. And on the front side, the crosses represent all the components we need to remove to achieve the D+ and D- paths shown on the back side. Now we can begin the controller swap. So here's what the final board looks like with all of the connections in place, and I've just put on the Debug USB cable, and let's see what happens when we can plug it in. I've got a D message trace here so we can see the behavior. Very nice. So at this point we can start building a QMK keyboard definition, but our matrix is still unknown, so we need to identify the keyboard layout to map physical key locations to matrix scan locations. For this board, we also need a custom matrix scanning algorithm to set the decoder and mux chip inputs instead of direct column and row pin mappings. So I've implemented the code in the custom matrix scan routine here. Recalling the basic matrix scanning algorithm discussed in the beginning of the video, we can also keep most of the QMK default logic the same and insert the row and column select functions in place of enabling the pins directly on the read columns on row function. There's a bit more to it than just this, including adding some extra preprocessor variables, but I'll link the source code for this in the description for those that want to use the same idea for another keyboard. The next step is to enable matrix debug so that we can output matrix scan information to HID debug in order to determine the layout. I'll first create a debug key map with all the key positions as default and the corresponding macro in the keyboard header file. So I've got an instance of HID listen running for the debug console that we've enabled on our QMK firmware, and I flashed it to the board. And now when I press keys, I can determine the location on the matrix grid. As you can see here, this one's, for example, 4-7. This one is 4-4, and we repeat this for every single key on the keyboard until we can find the location of the entire layout. As you can see, it's a very therapeutic process. In the end, the matrix mapping with a normal QMK key map looks something like this. Now we can flash the final firmware without console debug.